Okay, good morning Year 10, Mrs. Allbone here. I hope you're well and keeping safe. Welcome to your second physics lesson this week for the triple course. Today we are looking at resolution of forces. This is carrying on from the parallelogram of forces that we did earlier. You can see on your screen we have the key facts which we are going to cover in this lesson. They should be familiar to you because I have lifted them straight out of your fact book. Before we do that, I would like you to look at this starter. These questions are based on my last lesson, so I'd like you to pause the video and have a go at doing these starter questions now. Okay, so hopefully you've had a go at doing the starter questions. The answers are on the board. Again, I'd like you to pause the video and just check that you are happy with those answers before we carry on any further. Okay, so last lesson we focused on how we can work out the resultant vector if an object is acted upon by two vectors or two forces that are not acting along the same line, and we saw how we could add those two vectors together to get a resultant vector, and we did that largely by using a method called the parallelogram of forces. But we could actually be given the resultant vector and then be asked to resolve it into a vertical and horizontal component, and this is a method that's actually quite useful in engineering that people would do a lot of the time. So what do we mean by that? Well, if we have a vector, and you can see I've specified a scale there as well, so if we were to measure that out we would be able to work out how many newtons long it is. Now if we were to resolve that vector into a vertical and horizontal component, it would look something like this. So a horizontal component would be along the bottom there, and our vertical component would be at 90 degrees to it here. So we would have our vector resolved into a horizontal component and a vertical component, and then we could specify an angle between it there. Okay, so how would we do that? Well, to resolve a force into two perpendicular directions, you would actually take your vector and draw a square or a rectangle around it, and then that would give you your vertical and horizontal components. As it says, use scale calculations and then you'll be able to work out the magnitude and the direction of the force. So this is what I mean. So here's your resultant vector that we're starting with. So if you draw a rectangle or triangle around that vector, starting at your starting point here, and then joining up the vector with the end of the resultant vector here, you've made a nice square. So now that immediately gives you your horizontal component, which is here, and your vertical component, which is here. Okay, so if you think about it, what we did last lesson, if we were given two vectors, a vertical vector here and a horizontal one here, and we had a point object here, and we were asked how would that object move if these two vectors acted upon it. Well, from our last lesson you remember how we add those vectors together. So we would draw in our first vector, and then at this point we would draw our second vector, and then you would join them together at the start of the first vector to the end of the second vector, and that would give you your resultant vector. And all we're doing here is the opposite, resolving it into its vertical and its horizontal components. Okay, so pause the video and have a go at doing this vector yourself. So I want you to take that vector of 10 newtons at an angle of 37 degrees to the horizontal, and I would like you to draw that out and then resolve that vector into a vertical and a horizontal component. So pause the video and have a go at doing that now. Okay, so hopefully you have drawn something like this. So here we've drawn the vector in at the appropriate angle of 37 degrees, and then starting at the base of the vector, drawing a horizontal line that goes all the way around the vector from start to finish. And when you've done that, that gives you your horizontal and your vertical component, because your horizontal component is going to be along the bottom there, and your vertical component is going to be straight upright. And if you have drawn that accurately, you should have found that your horizontal component is 8 newtons and your vertical component is 6 newtons. So if you had an object at this point and you pulled it with a force of 8 newtons in that direction and 6 newtons in that direction, the movement that that object would experience would be 10 newtons at that angle of 37 degrees. Okay, there's nothing to stop you making your own vectors up. You could try a couple more of those just to practice drawing them out. Okay, what I want us to think about now is looking at an object on a slope. So if you have an object on a flat surface, imagine an object on a flat surface. Now you know that that object is going to exert a downward force, and that downward force will be due to gravity, and we call that downward force its weight. So there we have an example of a weight, a box, and that has a weight of 50 newtons. If you then tilted that surface so it was flat, and then you just tilted it so it went completely vertical, then what would happen? Well, we know that object would fall, and it would all fall with a force equal to its weight of 50 newtons. That much is obvious. Okay, so if, however, we take our object and we tilt the angle through a smaller, we tilt the surface through a smaller angle, so we know that that box will still slide down the surface, and it will slide down due to its weight, but this time it will slide down with a force that is actually less than that weight of 50 newtons. The force of 50 newtons will act straight down, but the part of the weight that's sliding it down the box will only be a small part of that total value of 50 newtons. Okay, so let's explore that a little bit more. So, tilt the box through a small angle, it will still slide down the surface due to its weight. But only some of the force is making the box slide down the surface. And we say this force is parallel to the slope. So this bit here. So part of this box's weight is parallel to the slope, and that's the bit that makes it slide down the surface. Some of the force makes the box press into the surface. So do you remember when the box was flat on the slope? The weight pushed into that slope completely. So now part of the weight is still going to make that happen, and we say that that is perpendicular to the slope. So you can see that we have part of the weight making the box slide down the surface, and we have part of the weight pressing the box into the surface of the slope. Now together, these two forces make up the box's weight. Okay, and there's our weight of 50 newtons. Now, this obviously explains why it's harder for a cyclist to bike uphill rather than cycling on a flat surface. So here, a cyclist is going along on a flat surface, his weight is acting straight down, but on a flat surface, the force of the weight is vertically downward. So he's not actually doing any work against that force. But if he then cycles up a slope, then that's different, because now part of the weight now has a component that's parallel with that slope, and part of that weight is going to try and make him slide back down that surface. So he's going to have to do more work to actually pedal uphill instead. You can see you've got that component pushing him down the slope. Okay. Now you need to be able to draw these forces accurately, and you need to be able to consider an object on a slope and how that looks and how you can draw it. So don't be alarmed by this diagram. Let's just talk ourselves through it. Now remember, it goes without saying, you need to have a pencil, ruler and a protractor. You cannot draw these diagrams accurately by guessing lengths and guessing angles. You have to have that equipment. Okay, so if we have a box here and it's on that slope, but it's at rest on that slope, so it's not moving, and the slope is tilted through a particular angle here, we know that the weight of that box is acting straight down the slope. Okay, not at an angle, but just straight down. And now we can divide that weight into a parallel component and into a perpendicular component. So as we have in the diagram here, you start at the beginning of that resultant vector, and you can draw a box around that vector like that, with one line being parallel to the slope and one line being perpendicular to the slope, and that will give you the two vectors that you need for the weight. Okay, let's look at that in a little bit more detail. There is the weight acting straight down. Here is our parallel component, and here is our perpendicular component. And you can see how when we add that parallel and perpendicular component together, the result is the weight. So you can see, if we move that down to the bottom there, we've added those two vectors together. So we've drawn the first vector, and then at the end of that first vector we've drawn the second one, and then we add them together, start at the beginning and go to the end, and you can see how these two components are resolved to make up the weight of the object on the slope. So how do you draw that accurately? Because it's not an easy thing to do, and it takes a little bit of practice. So first of all, you would draw in the weight to scale. So you need to work out your scale that you're going to use and draw in that weight straight down accurately. Then the next easiest thing to do is draw a line starting at that vector and drawing it 90 degrees to your slope here. Now the angle of the slope here and the angle COB, which is this angle, they are going to be the same. Now at this point I'm not going to go into the geometry of that, but if you want me to at some point, then I can explain that, but I won't do that here. So for the moment, if you know the slope, then that angle is going to be the same. Once you've drawn that in, we know that the angle OCB has to be a right angle. That has to be a right angle between the two vectors. And so, therefore, you are able to work out this angle CBO, because these three angles added together have got to make 180 degrees, as is true of all right angled triangles. So where the lines CO and CB cross, that gives you your perpendicular vector and your parallel vector, and together they will make up your weight. Okay, so I have taken this example straight out of the physics book. You have a car of weight 12 kilonewtons and it's parked on a hill, and that's at an angle, that slope is 10 degrees, and it's asking you to find out the component of the car's weight that is acting down the slope. So I'd like you to pause the video and have a go at working that out. Okay, so hopefully you will have drawn something similar to this in order to resolve this weight into its horizontal and vertical component. So you can see the weight is acting straight down, and in this example they have drawn a box around that resultant vector. One line is parallel to the slope and the other line is perpendicular to that slope, and then you can see that the component of the car's weight acting down the slope is going to be this little bit here. Now if you worked that out correctly, you should have got a value of about 2 kilonewtons, and I've tried to draw that out myself accurately. You can see here we've got the slope of 10 degrees, there's our slope there, the weight acting straight down, which is 12 kilonewtons, so we know that perpendicular component is at an angle of 90 degrees to the slope, and we know that makes an angle of 10 degrees. So if you draw that line in, and then we know that this angle here has got to be 80 degrees because we are trying to make a right angle here. So 10 plus 80 is going to be 90. That will give a total of 180 degrees. So if you draw your angle in here of 80 degrees and then draw your line of 80 degrees in, where they cross you should find that is a right angle, and then you can measure that distance and you should find it's 2 kilonewtons, and my scale was 1 centimetre equals 2 kilonewtons, and so that indeed was 1 centimetre long. You could, if you wanted to use some geometry to back that up and check it, by knowing your sine rule. Here is your adjacent line, and here is your opposite line, and here is your hypotenuse. So we know that the opposite, which is our value x, divided by the hypotenuse is equal to the sine of the angle, the sine of 10 degrees. And if you work that out, you will find that that comes to a more accurate value of about 2.1 kilonewtons. Okay, so not an easy technique to master, but quite straightforward once you have got the basics at your fingertips. It's just a little bit of practice needed. Now, one last thing that I want to mention is if you have an object on the slope and the object is not moving, what can we say about the forces acting on that object? Well, obviously we can say those forces are balanced, which is what you learnt with Mr. Pancholi last week. Doesn't mean there are no forces acting on that object, it just means the forces are all equal and the resultant force is 0. So in this situation, if you have an object on a slope but it isn't moving, then those forces are balanced, and we can say the following. The perpendicular component of the weight is going to equal the normal contact force of the slope. So remember I said the perpendicular component of the weight pushes the box into the slope, and with every reaction we have an equal. With every action we have an equal and opposite reaction, so the slope is going to push back with an equal force, and that's called your normal contact force. At the same time, the parallel component of the weight is going to equal the friction of the slope, which is stopping the object from moving down the slope. So here we have our parallel component of the weight trying to pull the object down the slope, but if the friction of the slope is great enough, then that object is not going to move. So we would say that the frictional force holding it in place is equal to the parallel component of the normal contact force. And it's really important that you appreciate that force diagram. Okay, so that really covers the content of today's lesson. I have now put up the summary questions, which I've taken straight out of your AQA book, and I would like you to spend a little bit of time drawing these force diagrams out and answering these questions. So pause the video and have a go with them. Okay, so here are the answers to those questions, which hopefully you have managed to complete. I don't think there is anything too tricky there. I have written out my own answers to them, so you can pause the video on each one just to look at the diagrams that I have put together. For the first one, if you think about the wind pressing down on the plane, so that would be the point where the nose of the plane is, and you have got the wind, the force of the wind pushing at that angle of 30 degrees on the nose of the plane. So you can resolve that vector of 800 newtons into a horizontal component and a vertical component, and by using an appropriate scale you should be able to work out both the vertical and the horizontal component, whichever one was needed. Looks like the horizontal component was needed in this answer. For the second one, we have the weight acting straight down, which is 510 newtons, and this slope was an angle of 15 degrees. So again, we draw our perpendicular line, which is at right angles to our slope, draw that in, and we know that the angle between that line and the weight is going to be 15 degrees, exactly the same as it is here. So we draw that line in. If that's 15 degrees and we're wanting to make a 90-degree angle here, then we're able to work out the value of this angle and measure it. And then you draw a line at that angle, and where they cross, that point is at 90 degrees. And we know that the vector pushing the object down the slope, or pushing the trolley back down the slope, is going to be equal to this vector here. With the third question, obviously if the friction on the floor is too slippery, then there's no horizontal force to oppose the weight of the ladder pulling the ladder down. So you would need a frictional force pushing from left to right to hold that ladder in place. And if it's too slippery, then it's not going to do that and the ladder is going to fall down the slope. And then finally, you were asked to draw this box out, draw it out accurately at an angle of 30 degrees, which is the slope. So we know if we draw our perpendicular line in, that angle will also be 30 degrees. If that's 30 and we're trying to make an angle of 90 degrees here, this one must be 60. So if you measure from the weight that angle and draw a straight line across, where they cross will give you your right angled triangle. And again, your component of the weight that moves it down the slope is going to be equal to that component there, and the perpendicular component pushing the box into the slope is going to be this distance here, which you can measure and you can check by using your sine and cosine rule. Okay, year 10. So quite a lot to take on board there, but it is quite straightforward and it's just a little bit of practice to get you feeling comfortable with doing this. And these are the key facts that we need to cover for this lesson, which we obviously have done. So resolving the force is opposite to the parallelogram method. We need to draw a box around our resultant force to divide it up into two perpendicular directions, and we have also looked at resolving forces for an object that's stationary on a slope. Okay, so I hope you've enjoyed that lesson. Email me if you are struggling with any of this and I will get back to you. So enjoy the rest of your day.